Hi, my name is Tomer, and I'm here to present a joint work on an active learning scheme for neural networks-based receivers. What I would like you to take from this talk is how should one incorporate machine learning ideas in communication applications, taking into consideration domain knowledge relevant to the communication field. Okay, so this is the agenda for this talk. First, we'll cover the relevant background, explaining a bit about machine learning for communication. Then I'll present the problem setup, including the transmission protocol and the channel. Lastly, I'll explain what active learning is in general, and specifically what is the motivation for incorporating it in the detection scenario. So let's begin. Wireless data traffic have grown exponentially over recent years with no foreseen saturation. 6G communication will require high adaptivity to both new channels and new environments. We consider the detection scenario presented here with a transmitter, a channel, and a receiver. We indicate that real channels are nonlinear and change constantly due to many different components. Such a complex environment can motivate researchers to incorporate machine learning into classical communication blocks, including detectors, which is the focus of our work. We note that there's a big difference between conventional deep learning applications in vision or in NLP versus the application to physical layer communications due to both the dynamic nature of wireless channels as well as the need to achieve near optimal performance. An assumption that machine learning makes is that the training distribution matches the test distribution. Obviously, this assumption is hard to make at many domains, and specifically at communications where the distribution can change frequently. The question that we are set to ask is, how should one facilitate adaptation of a machine learning detector in a fast varying environment? Before getting to the approach, let me present several assumptions. First, the channel has a memory of L, meaning that Y, the received channel vector, depends on the current and L-1 previous symbols, where a single symbol is denoted by S. This is a widely used model for representing multipath channels. Additionally, we transmit in words or blocks of bits, and the channel follows a Markovian relation as presented here. Our detector is given by the mapping S hat, and its goal is to minimize the symbol error rate over all transmitted bits. Well, the maximum likelihood detector for this case is the Viterbi detector, which is also very efficient and works in linear complexity over the block. But it has maximum likelihood performance only when the branch metrics are calculated accurately. And this assumes full channel state information, full CSI. In real scenarios where one assumes a linear Gaussian channel, degraded performance is to be expected. Thus, to learn the channel statistics on the fly, another approach was suggested, named ViterbiNet. ViterbiNet keeps the same basic architecture of Viterbi, but replaces the probabilities calculation with a neural network, learning the mapping to states from the data itself. Now, we have the required background to present the problem that we deal with in our paper. As the channel changes with time, the neural network aided Viterbi net must be retrained and adapted to minimize the overall symbol error rate. This has to happen during a typical transmission scenario as depicted here, where multiple data blocks are transmitted sequentially. The receiver has no knowledge of the ground truth transmitted symbols. Well, one naive solution for this case is frequent transmission of pilots over the channel, but this is costly and induces spectrum overhead. Another solution is to estimate the channel coefficients and use them in the detector as features, but this assumes a Gaussian linear channel, losing the expressive capabilities of deep learning. Thirdly, and a preferable solution is that one can detect the transmitted block with a current receiver and use its estimation as data for retraining as depicted at the bottom. But as the channel varies, some symbols are labeled incorrectly. Training on mislabeled data quickly leads to the divergence of the detector. Our approach is designed to heuristically select those symbols which have a high probability of being labeled as correct by tailoring an active learning scheme to this specific case. But first, what is active learning? Well, active learning is a supervised learning method which deals with an oracle that actively chooses the samples from a large pool of data to feed a model. The conventional motivation is that a properly queried batch can benefit the training more than using the entire unfiltered dataset. To select the queried batch, one can introduce a measure that quantifies how informative is any given sample, inducing some ranking among them and training with those that are most informative. We adapt this notion of active learning to our case, where we query the most informative samples for training out of the data block itself. To define such a measure, we use the soft output of Viterbi net. After passing the observed channel value once through Viterbi net, we can calculate the cost per state, where the cost is defined as minus this likelihood here that is presented. Then we introduce the soft gap GI as the absolute difference between the minimal and second to minimal costs. If the detector is unsure about its decision, we expect to have two different states with costs close to each other, and vice versa. If the detector is absolutely confident in its decision, this value will be high. This measure is also combined with two innovative diversity principles, reliability diversity and symbol diversity. High reliability magnitude usually means that a sample incorporates low noise realizations, while on the other end, low reliability means that a sample is too noisy to learn from. Thus, we rank higher those samples that are of medium reliability. Considering the symbol diversity on the right, one has to balance the number of samples per class so as to reduce the probability of overfitting on a specific one. Thus, we choose batches that are balanced in terms of per class samples. To sum up, our approach considers 3 building blocks: the confidence gap, reliability diversity, and symbol diversity. These blocks guide the oracle in choosing the subset of samples that are fit for training. Please refer to the paper for a full description of the algorithm itself. Okay, so moving to results, we used a channel with 4 taps over a transmission of 200 blocks, each having 2000 BPSK symbols. We compute the symbol error rate per block, showing only the results over the first 25 blocks. Our method, referred to as median training, is compared with this full CSI Viterbi, a Gini-aided Viterbi net that has knowledge of the ground truth symbols, and some naive baselines, including training with higher or lower values of confidence gap. You can see that our proposed method, depicted here, surpasses all common training techniques, closely mimicking the performance of the Gini. This work serves as an example of one of the cornerstones: architecture, training algorithm, and data, all related to adapting neural networks in time-varying scenarios. While ViterbiNet targeted the architecture, and our previous work on MetaViterbiNet presented at ICC targeted the algorithm, we targeted here the data aspect. For conclusion, our main contribution is an active learning technique tailored to neural-based detectors. This technique aids the detector to adapt in scenarios where the channel varies rapidly. Please refer to our paper for more details, and we also published our Python code on GitHub, and you are welcome to check it. Thank you.